Estimating the electric potential of a chemical solution. That's what we decide to work on. The problem. With numerous research going on to study the functioning of the brain, which is the powerhouse of the human body, the brain can be modeled as a membrane with composite biological electrolytic solution. To better understand the working of the brain, we try to ascertain the electric potential due to the solution containing billions of neurons and charged ions. The question is, why should we do this? We're doing this to better understand how the brain works and how this understanding, and with this understanding, we can assist researchers in solving various brain-related health problems, and also better design of electrolytic cells and electronic devices or other applications that this study will lead breakthrough on. How do we estimate the electric potential due to a solution with several ionic constituents? Is another question. This can be done based on the general concept of electrochemical activity of ionic particles and the application of Nernst law, which we will see in detail on later slides. The concept used for this analysis is based on the general concept of electrochemical activity of ionic particles, the application of Nernst law here, which we will see in details later on. The electrochemistry is concerned with the interrelation of electrical and chemical effects. It's a broad field of electroanalysis, sensors, energy storage, conversion devices, corrosion, electrosynthesis, and metal electroplating. There are two general types of electrochemical methods. We have the potentiometric, no current equilibrium potential. We have the voltammetric, current measured as a function of the applied potential. Also, electrochemical cells, we know, consist of two electrodes, the anode and the cathode. The anode, the electrode where oxidation reaction occurs, and the cathode where reduction reaction occurs. These two reactions occurs in pairs, as we know, and the equation, chemical equation we can see on the slides, is just representing the oxidation of copper and the reduction of zinc. We know copper has a greater electrochemical activity compared to zinc, hence oxidation of copper and the reduction of zinc. And we also know there are two types of electrochemical cells, the galvanic cells and the electrolytic cells. Electroanalytical chemistry encompasses a group of quantitative analytical methods that are based upon electrical properties of an analyte solution when it is made part of an electrochemical cell. The method makes possible the determination of a particular oxidation state of an element. There are two types of electrochemical cells, the galvanic and the electrolytic. The galvanic spontaneously produces electrical energy, and the electrolytic consumes electrical energy. And this is a diagrammatic illustration of both processes. But here we are concerned about the galvanic process because we are going to measure the activity, try to measure the potential due to the activity of the constituents of the solution. So the galvanic is a better modelization of the problem. In this analysis, just like I just said, we are considering potentiometric and galvanic solution, which is the most appropriate modelization for the resting potential membrane of the brain. We consider a relatively static solution in a state of chemical equilibrium.
Let's move right now to the Nernst equation. Why is it very important to know about this equation? With the Nernst equation, we can model the potential in general given one ion in a solution. Before showing the equation, it's very important to know the assumptions needed to apply it. Nernst made certain assumptions that one must be aware of when using this equation. Those assumptions are: first of all, this equation can only be solved for one ion at a time, either sodium or potassium, but not both. The membrane must be completely permeable to that ion. Finally, the ion must be at equilibrium. Remembering these assumptions, we can show the Nernst equation defined as follows: E equal to RT over C F logarithm of ion outside cell over ion outside cell. R is the ideal gas constant in joules per Kelvin per mole. T is the temperature in Kelvin, a key point when you measure the potential. F is Faraday's constant in coulombs per mole, and C is the valence of the ion. But what ion outside cell and ion inside cell mean? The component ion inside cell is the intracellular concentration of that ion in molecules per cubic meter. And finally, ion outside cell is the extracellular concentration of that ion in moles per cubic to match the other SI units, though the units strictly don't matter as the ion concentration terms become a dimensionless ratio. Let's see right now an example. Let's suppose that we have a solution, and inside this solution we have multiple ionized particles. But let's do our example only for one of those particles. We consider a particle through the abstraction of an ideal sol with a big potassium concentration inside. If we have a big potassium concentration inside the cell and a low concentration outside, we can affirm that this will generate a concentration gradient that will force the potassium particles to flow. Specifically, we will have potassium particles moving, therefore we have positive particles flowing too. It's this capacity of the ion particles inside the solution to move what allows us to talk about an inherent ion potential in relation with the other ions. We can use this basic but powerful idea to find the total electric potential in the solution.
Okay, now I will introduce something about the multiply ions particularly. As what he has said, the Nernst equation is very useful for electric potential, but there is only a kind of ion in the solution. Is that so simple? Of course not. The kinds of ion in the solution are very complicated. Maybe they are product, maybe they are reactant. If the concentration of ions changes, the electric potential also changes. So we have to analyze this situation. As you know, in a simple reaction, we can use Nernst equation to get the electric potential. So in this situation, we just need to expand our method. We can use two matrices. Every element in this matrix is the concentration of the ion in the solution. Because there are different ions in solution, so the matrix is huge. We need to use what we learned in the class, fast computing solver. The first situation is independent. As we can see, there is two chemical reactions. The first one is two nitrogen plus plus hydrogen, and the second one is methane plus oxygen. So we can see that the reactant of the two different chemical reaction is different, so they can happen at the same time. Even we mix hydrogen and nitrogen, they don't have, because there are no chemical reaction happened, so they don't have impact on calculating the electric potential. In this situation, the matrix, there is a lot of zero in its element because they can't have a chemical reaction, so this matrix is sparse. Okay, the second one is product and reactant. The left photo, the chemical reaction is two hydrogen plus one oxygen. We get to water, but the water is also a reactant in the next chemical reaction. So the matrix is more difficult. The reaction product is a reactant in another chemical reaction. In this situation, the matrix maybe is 4 rank and not sparse, and how to solve this problem is a question. The second one, competition. In this situation, a kind of ion are reactant of two different chemical reactions. At this time, in general there is a strong chemical reaction and a weak chemical reaction, but they are happening at the same time. The matrix is complicated, so we can see that there is a three situation. We can't just use a simple model to analyze it. If the model is incorrect, we cannot get a correct electric potential. So all in all, the situation in the solution are complicated, and the mathematical model should adapt it very well. The next person will explain how to set up a mathematical model to analyze this situation.
As we have seen before, the huge amount of data makes it very hard, even for a computer, to model and yet to follow a real ongoing pattern. If computers were infinitely fast, any correct method for solving a problem would do. You would probably want your implementation to be within the bounds of good software engineering practice. For example, Your implementation should be well designed and documented, but you would most often use whichever method was the easiest to implement. Of course, computers may be fast, but they are not infinitely fast, and memory may be inexpensive, but it is not free. Computing time is therefore a bounded resource, and so is space and memory. We should use these resources wisely, and algorithms that are efficient in terms of time or space will help us do so. That's why finding those algorithms that calculates the operations in a reasonable time is necessary. They are called the fast solvers. Computational complexity theory is the study of the complexity of problems, that is, the difficulty of solving them. Problems can be classified by complexity class according to the time it takes for an algorithm, usually a computer program, to solve them as a function of the problem size. Some problems are difficult to solve, while others are easy. The Big O notation characterizes functions according to their growth rates. Different functions with the same growth rate may be represented using the same O notation. We need the linear time, which is a no n. It is an algorithm that is directly proportional to the input size, while the quasi-linear time is a performing O log n operations that are made in time, and the fast solvers are algorithms that have one of these two complexities. In the case of independent reactions, the matrix representing the pattern would be sparse, which makes it easier to implement, since the storage would take less space and ergo less time. The algorithm will have hence a linear or a quasi-linear complexity. In fact, storing only the non-null elements will change the situation from dealing with a whole matrix to dealing only with few vectors, which will give a linear complexity to matrix multiplication that have normally a square one. The other case is if the reactions in the solution are not necessarily independent, but have instead a clear structure that is repeated continuously. Such case will give us a structured matrix. So all that's left to do is to recognize the structure and again store only the vectors that are responsible of it, and we will find ourselves in a similar situation as the first one. The hard case is when having a full rank non-structured matrix. This will occur in the situation of a solution with totally random reactions. Due to the complexity of the resultant matrix, we will need to use the singular variable decomposition, SVD, which is an algorithm that gives an approximation of the matrix but with the optimal error, except that such algorithms have a cubic complexity, and this is a very expensive cost. Therefore, for faster computation results, we will use a fast algorithm solver that gives accurate and similar results as the SVD, but with a cheaper cost. That's why it is called the cheap SVD.